Hydrogen cracking in pipelines can lead to leaks, ruptures, pipe replacement, and lost revenue. So what causes hydrogen cracking, and how can it be avoided? Unlike workmanship defects, such as slag inclusions, porosity, and undercut, hydrogen cracking is independent of the welder's skill. Instead, it depends on the materials, welding process, procedure, and the environmental conditions. Hydrogen cracking, also called hydrogen-induced cracking, hydrogen-assisted cracking, cold cracking, delayed cracking, and under-bead cracking, typically occurs at stress concentrations, such as the root or toe of the weld, and can propagate through the weld metal or heat-affected zone. Hydrogen cracking results when three independent conditions occur simultaneously. Hydrogen in the weld, a crack-susceptible microstructure, and tensile stresses acting on the weld. If one or more of the conditions are removed or reduced below a threshold value, hydrogen cracking will not occur. Because the susceptibility to hydrogen cracking increases with increased hydrogen content, this demonstration video will focus on limiting hydrogen in the weld. Welding processes, such as shielded metal arc welding with AWS 18 type electrodes, gas metal arc welding, and gas tungsten arc welding, are considered low hydrogen welding processes. The hydrogen content of a weld is measured in milliliters per 100 grams of deposited weld metal. A typical low hydrogen process produces welds with 4 milliliters of hydrogen per 100 grams or less. In contrast, shielded metal arc welding with AWS 10 type electrodes results in welds with hydrogen levels of 40 to 60 milliliters per 100 grams. That's 10 times more hydrogen. If a weld remains at high temperature after welding due to preheat, interpass temperature control, or post-heating, the hydrogen that was introduced into the weld has the ability to diffuse away. This is because the average diffusion rate of hydrogen in steel at 100 degrees Celsius or 212 degrees Fahrenheit is typically 1,000 times faster than at 20 degrees Celsius or room temperature. In addition to preheat, the wall thickness of the joint and number of weld passes has an effect on the diffusion of hydrogen from the weld. The following three animations, provided by BMT Fleet Technology Limited, show the hydrogen level for welds made on 1/4 inch and 5/8 inch thick pipe materials without preheat, as well as a weld on 5/8 inch thick pipe material with a 250 degree Fahrenheit preheat. The hydrogen levels are modeled after a typical cellulosic-coated AWS 10 type electrode. The hydrogen is introduced during each weld pass and diffuses into the heat-affected zone, base material, and surrounding atmosphere as the weld cools. The maximum hydrogen levels present 3 days after welding are 1.75 milliliters per 100 grams for the 1/4 inch thick pipe and 10.5 milliliters per 100 grams for the 5/8 inch thick pipe. The 250 degree preheat for the thick-walled pipe allowed more hydrogen to diffuse away and lowered the maximum remaining hydrogen level to 8.75 milliliters per 100 grams. Post-heating following the completion of welding can further reduce weld hydrogen levels. Hydrogen can come from sources other than the welding process itself. It can be introduced by organic materials or moisture that are either on the electrodes or on the materials being welded. Hydrocarbons and water can break down into atomic hydrogen in the intense heat of the welding arc, which is readily absorbed by the molten metal. This is because the liquid weld metal has a very high solubility for hydrogen. But as the weld solidifies as it cools to room temperature, the hydrogen becomes trapped or supersaturated in the solid steel. You may be wondering how hydrogen can be trapped in the weld metal if no bubbles or porosity are evident. Let's look to the periodic table. Iron, the main element in steel, has a relatively large atomic size compared to the small atomic size of hydrogen. If you imagine the iron atoms are basketballs and the hydrogen atoms are ping pong balls, it becomes apparent that hydrogen atoms can fit into the spaces between the iron atoms. The following shielded metal arc welding demonstration will show the differences between a cellulosic-coated, high-hydrogen AWS 10-type electrode and a basic-coated, low-hydrogen 18-type electrode. The low-hydrogen electrode used has the designation H4R, meaning the hydrogen content of the as-received electrode is 4 milliliters per 100 grams or less, and it is covered with a moisture-resistant coating. The importance of proper maintenance of low hydrogen electrodes and the benefit of preheat is also demonstrated. Bead-on plate welds are being deposited using the shielded metal arc welding, or stick welding, process. Immediately after completion, the welds are placed into mineral oil, so the diffusion of hydrogen from the completed welds can be seen. The first sample was welded with a cellulosic-coated, high-hydrogen electrode and placed into room temperature mineral oil. A large number of hydrogen bubbles can be seen slowly diffusing from the weld. The second sample was welded with a low hydrogen electrode. Compared to the first sample, much less hydrogen diffusion is evident. This coincides with the fact that approximately 10 times less hydrogen will be introduced to a weld made with low hydrogen electrodes, compared to traditional cellulosic-coated electrodes. The third sample was welded with a poorly maintained, low hydrogen electrode that was allowed to absorb moisture. Despite the moisture-resistant coating, we can see a large number of hydrogen bubbles diffusing from the weld, similar to the amount seen in the high hydrogen electrode. Preheating, interpass temperature control, and post-heating can be beneficial in increasing the diffusion of hydrogen out of completed welds. The weld made with a high hydrogen electrode was allowed to sit at room temperature until the majority of the hydrogen diffusion possible was complete. When it is placed into mineral oil that is heated to 250 degrees Fahrenheit, a temperature that we showed allows hydrogen to diffuse 1,000 times faster than at room temperature, we can see that diffusion begins again and a rapid release of hydrogen occurs. Therefore, welds that are preheated and allowed to slow cool or post-heated will allow more hydrogen to diffuse, reducing susceptibility to hydrogen cracking. So remember, limiting hydrogen in the weld can reduce the hydrogen cracking susceptibility. We've demonstrated. Low hydrogen electrodes introduce a small amount of hydrogen into the weld. However, improperly maintained low hydrogen electrodes can introduce approximately the same amount of hydrogen into the weld as high hydrogen electrodes. Finally, if it is not feasible to significantly limit the amount of hydrogen that enters the weld, careful control of preheat, interpass temperature, or post-heat increases hydrogen diffusion and reduces cracking susceptibility.